Now we need to look at the question of whether ultrasound is safe, or under what conditions we can consider ultrasound to be safe. Obviously, one of the things that helps is to look at history. If we look at the history of X-rays, at first they were thought to be quite safe and harmless. But of course, later in life, people developed symptoms which eventually were connected with exposure to X-rays. The history of ultrasound is very different. Most statements on the safety of ultrasound begin by saying something to the effect that there has never been a documented case where a patient has been harmed by exposure to diagnostic ultrasound. That's an excellent thing to be able to say. It's a very, very good safety record. In addition, ultrasound is non-ionizing. This means the energy levels in the ultrasound wave are not sufficient to affect tissues at the atomic level, and that means that many of the mechanisms that are relevant to X-rays, nuclear medicine, etc., don't apply to ultrasound. Nevertheless, ultrasound would not be useful to us unless it interacted with tissues. Here's an example of the therapeutic use of ultrasound energy. Physiotherapists use high-intensity ultrasound to heat tissues in order to promote healing. They're using an effect which we consider to be an unfortunate byproduct of diagnostic imaging, the heating of tissues as ultrasound travels through those tissues. It always occurs. I spoke about this when I was talking about the attenuation of ultrasound. It's due to the absorption of ultrasound energy, and it is converted to heat. So physiotherapists are using this heating effect therapeutically. Another example is the lithotripter. This device uses high-intensity, highly focused pulses of ultrasound to shatter stones like renal stones, for example. The idea is the stones are broken up into fine particles which the body can then excrete. So clearly, high-intensity ultrasound can produce effects that would be potentially harmful. So we come back to the question of whether diagnostic ultrasound levels are safe. And unfortunately, it's not possible to prove that. It's never, in fact, possible to prove that something like ultrasound exposure is safe. There's always the possibility of some effect that we haven't anticipated and haven't looked for. So we can't prove that ultrasound is safe. If it was a new test or therapy, we would use randomized controlled trials to look at its safety. This is simply not feasible for diagnostic ultrasound today because it would not be ethical to withhold ultrasound from a large number of patients in order to have a control group. In the early days of ultrasound, there were small randomized trials of safety, and they indicated no evidence of harmful effects, but they were too small to be really definitive. So for these reasons, we have to follow what's called the precautionary principle. And this essentially means that we believe ultrasound is likely to be safe at clinical levels, but we can't be absolutely certain, and so we treat it as if it might be potentially harmful. How do we characterize exposure? Well, at the basic level, we have the total amount of energy, ultrasound energy, delivered into the patient's tissues. If we're interested in the rate at which this is happening, then we would look at power, which is the amount of energy per second. But from the point of view of safety, the most useful parameter is intensity, which looks at the power per square centimetre area. So think of a picture like this. The intensity is the amount of energy per second flowing through an area of 1 square centimetre. So this is a measure of the actual exposure of a particular piece of tissue, not averaged over any large area. It's the localized exposure level. Calculating the intensity is not simple. After all, we have to look at both time variation and spatial variation. So here on the left, I'm looking at the time variation of the transmitted energy. We have a transmit pulse, then a long period of time where no energy is being transmitted, and then the next transmit pulse. So if you look at the bottom of this diagram, you can see the intensity calculated from these transmit pulses. And I'm indicating 3 different commonly used intensity measures. The largest of these is the temporal peak intensity. So that's the instantaneous maximum intensity value at the peak of the transmit pulse. Then we have the pulse average intensity, which is averaged over the duration of the transmit pulse. And then much, much lower, we have the temporal average intensity, which is the intensity averaged over a complete transmit cycle. Now, which one of these is relevant depends on the situation. If we're talking about heating, then the temporal average value would be the relevant one, because heating occurs over a period of many seconds, and it's the amount of energy delivered over that time that determines how much heating occurs. So the temporal average would be the relevant factor. As well as time variation, we have spatial variation of the intensity. In the top half of this diagram on the right, you can see the way the intensity varies as we move away from the probe face deeper into the tissues along the center line of the beam, the axis of the ultrasound beam. So you can see there are fluctuations in the near field, and then we reach a maximum at the point of focus. Now, if we look at the lower part of this diagram, I'm showing the way the intensity varies at the focal depth across the beam. So we're going laterally across the beam. And of course, this is the profile that you've seen before. And what we see is that the intensity is maximum in the center of the beam. So we have a spatial peak value in the center of the beam at focus. Now, I've talked about various different measures of both the temporal intensity values and the spatial values. These are combined together into various different measures. So at the top of this chart, we've got the spatial peak, temporal peak intensity. So that would be the instantaneous maximum intensity at that one point at focus where the intensity is greatest. So that would be the largest possible intensity value anywhere. Then we have various other combinations, and at the bottom of the chart, we've got the spatial average, temporal average intensity, which is very, very much smaller because it's averaged over time and also over space. So these are various values that you will see quoted in safety guidelines, the manufacturers' specifications, etc. So, in summary, there are good reasons to think that diagnostic ultrasound is safe, at least as long as we have reasonable exposure levels. And we'll need to talk more about what I mean by reasonable exposure levels. But remember, we can never prove that ultrasound is safe, and therefore we adopt that precautionary principle. And I'll talk more in a later lecture about how we put that into effect. And then I've just highlighted the fact that measuring and characterizing the exposure is somewhat complex.